Welcome back. In this video, we're going to talk about differentiating and integrating Fourier series, and also in a warm-up exercise, and we'll use it later in the lecture, what I'll call uniqueness of Fourier series. Okay, and so the warm-up exercise will explain what I mean by that. So consider a function little f of t equals 4 minus 3 sine 2t plus 2 cosine 3t. That's 2 pi periodic because sine 2t has period pi and cosine 3t has period 2 pi over 3, and multiples of those are 2 pi. So the question is, what's the 2 pi periodic Fourier series for f? And remember, in Fourier series, there are a series of sinusoidal functions whose periods are fractions of the natural period, or in this case, the omegas are all integers. Do you know the answer? Here's the answer. This formula is the Fourier series. For f. Now, you have homework problems like this, and you might be tempted to do this the long way, which is compute all the Fourier coefficients, and this is what you'll get. Okay, but let me explain the reason why you don't have to go through that trouble. So one reason why you don't have to go through that trouble is, remember that for the set of functions that I called capital Vn, spanned by 1 cos t up to cos capital Nt, and sine t, sine 2t up to sine capital Nt, was an orthogonal set. So those functions were automatically a basis for V capital N, and we had the projection formula, and we checked that the projection of any f onto V capital N gave us, why don't we call it capital Fn, which is the truncated Fourier series, where we add up the terms to cosine nt and sine nt. So that's where the Fourier coefficients came from. And projection onto, orthogonal projection onto a subspace leaves the subspace fixed. So the projection of any function, say g, onto Vn is itself if g is already in V capital N. Well, our f is contained in V3, which is contained in V4. It's contained in all the capital Vn's, where n is at least 3. And so when we project, we'll get the truncated Fourier series. The functions in this set are linearly independent, so the weights are unique. So the projection of our f onto V capital N is always 4 minus 3 sine 2t plus 2 cosine 3t. Those are the Fourier coefficients for the corresponding sinusoidal functions. And this argument actually extends for infinite sums of sinusoidal functions. So if f is given by an infinite series made out of constant cosine nT's and sine nT's, and if, so that series has to converge in some sense, and the sense that we need is if the truncated Fourier series converges to f in the distance sense that we get from the inner product, and technically that means that the sequence is Cauchy if you've had some analysis, then the Fourier series for f is just the formula for f. Okay, so this is useful, as you'll see in your homework, and we'll even appeal to it today. Okay, so our main topic is differentiating and integrating Fourier series. And so to differentiate, we're going to want something which is differentiable, and precisely we're going to want it to be continuous and piecewise differentiable. So let me draw, and we actually want that on all of R when you extend your function to be 2 pi periodic. So what we want is that our function is differentiable on subintervals that you get by deleting a finite number of points. It's continuous everywhere it's not differentiable. And the one-side limits of the derivatives converge. So the derivatives have jump discontinuities at the continuous but not differentiable points. Okay, we want the whole thing to be continuous. So that means that the values at minus pi and pi have to match up. Okay, and then you can also think of the 2 pi periodic extension, where we go to the right and to the left. Okay, so that's what kind of functions we're going to be taking derivatives of, and our favorite example in class notes is the tent function, which was the 2 pi periodic extension of the absolute value function. Okay, so f prime is piecewise continuous and has jump discontinuities. All right, so then the theorem says, consider the Fourier series for f. Now, because f prime was piecewise continuous with jump discontinuities, it was one of these piecewise continuous functions, actually on all of R, but also on minus pi pi. So it has a Fourier series. And the theorem says you just compute it by differentiating term by term. So the derivative of cos nt is minus n sine nt. The derivative of sine nt is n cosine nt. So it's a very easy theorem to remember. and use as long as you are differentiating a function you're allowed to differentiate. And I want to explain why the theorem is true. So what we're going to do is kind of tricky. F prime has a Fourier series, so let's just write it down. Let's use capital letters. I'm realizing it would have been better to reverse capital and lowercase according to our conventions since calculus. But anyway, capital F prime has a Fourier series with capital letters. And let's compute the Fourier coefficients using the formulas. So just to remember, A naught, actually A naught over 2 would be 1 over 2 pi, integral from minus pi to pi of f prime of t, because it's f prime whose Fourier series we're converging, and bn would be 1 over pi, integral from minus pi to pi of f prime of t sine nt dt. And let's just focus on the capital A n's. So what I'm going to do is integrate by parts, and you can see I'm probably going to end up getting Fourier coefficients for f. So my dv, well, so my u will be cosine nt. My dv will be f prime of t dt. So du is minus n sine nt dt, and v is just f of t. Okay, so let's compute capital A n using integration by parts. There's a 1 over pi in front of everything. Then I get uv, which is cosine nt f of t, and we're going from minus pi to pi. Then I subtract off the integral of v du is f of t times minus n sine nt dt, close parentheses. Okay, let's look at these pieces in order. So cosine nt is 2 pi periodic. F of t, remember, is continuous on r, so it's and 2 pi periodic. So the product has one of its period as being 2 pi, so when I evaluate it at pi, I get the same thing as when I evaluate it at minus pi. So that term disappears. Then what's left? Well, I have a 1 over pi outside the parentheses. Inside the parentheses, in the second term, I have a minus and a minus. That gives me a plus. Then there is an n, which I'll take out of the integral, and I'm left with the integral of f of t sine nt dt. And I recognize the 1 over pi times the integral as the sine coefficient, the b sub n for little f. So capital A sub n is little n b sub n, and that's what I was trying to show. The capital A n, which is the coefficient of the cosines in the f prime, is n b sub n. Okay, and as I say, the arguments are exactly the same when you check that the capital BNs, which are the coefficients of the sines, are given by what you get when you differentiate the cosine terms, which is minus n little an. Okay, so that's the justification for differentiating term by term. So you can turn this argument around, or use this argument to consider when you can integrate a Fourier series term by term. Well, so you can integrate piecewise continuous things. So if I have piecewise differentiable, then I can differentiate the Fourier series and I get piecewise continuous, 2 pi periodic. If I want to integrate, I start with piecewise continuous and I'll end up with piecewise differentiable. And the theorem says exactly what you'd expect. So you start with such a little f, and then you can anti-differentiate term by term to get an antiderivative. So a naught over 2 has an antiderivative a naught over 2t. The antiderivative of cos nt is sine nt over n. Antiderivatives of sine nt are minus cos nt over n. And then you also get an additive constant. Okay, so if you want to just believe the integration theorem, you can skip my explanation. It's got a couple little intricacies, and so I wrote the proof down beforehand, and I'll just talk through it, and you can think about it if you need to take more time. So the first point is that because little f is piecewise continuous, the accumulation function, which you remember from calculus, it's how much little f accumulates between 0 and x, that's capital F of x, that's going to be continuous, because when you change the little x a little bit, the integral is not going to change very much because little f is piecewise continuous and bounded. So furthermore, by the part 1 of the fundamental theorem of calculus, wherever little f is differentiable, you can differentiate the accumulation function and you just recover the integrand evaluated at x. Okay, so therefore, the antiderivative of a piecewise continuous function is a continuous piecewise differentiable function, exactly the sort that the differentiation theorem let us differentiate term by term. Now, here's the subtlety. The accumulation function might not be 2 pi periodic. The only way it's going to be 2 pi periodic is if the net accumulation over any interval of length 2 pi is 0. But what you can do is you can subtract off a linear term to make it periodic. So you can subtract off, I call it capital AT, which is just the secant slope over an interval of length 2 pi times t. And then the capital F minus AT will be 2 pi periodic and piecewise C1. So it'll have a Fourier series for sure. And its derivative will be little f of t minus a. And because we have the differentiation theorem, we can compute the Fourier series just by differentiating term by term. Okay, and so let's look at what we've got here. So little f of t minus capital A, well, the little f of t has the a naught over 2, and it has the Fourier series the sinusoidal part of the Fourier series, and then I've subtracted capital A. So what I have on the left here is a Fourier series expansion, and on the right I have an equal Fourier series expansion, and so by uniqueness of Fourier series, when I look at the sine nt terms, I get this equality. And what that says is that the capital A n's are minus bn over n. And when I look at the cosine nt terms, I get that little a n is n capital Bn, or I can write it this way. And so that means that the sine coefficients for the antiderivative are an over n. And then when I look at the constant term on both sides, I see that a naught, little a naught over 2 is capital A. So that's this one. And that formula for capital F is exactly what we got when we integrated term by term. How's that for slick? Okay, so let's illustrate the theorem by just doing one example in both directions. So we know the Fourier series for the piecewise differentiable function tent is given by that formula. And we know that the derivative of the tent function is the square wave function, because the slope of those segments goes from -1 to +1 to -1 to +1. And so the theorem says, by the differentiation theorem, that the Fourier series for the square wave of t, I guess sometimes I call it square of t, sometimes I call squa of t, is just derivative pi halves is 0. Then I take -4 over pi, the sum over n odd. I didn't give myself enough room. Let's do it here. Tent prime of t is 0 minus 4 over pi, the sum over n odd of 1 over n squared. Derivative of cos nt is minus n sine nt. And the two minuses give me a plus. The n over n squared gives me a 1 over n. So that's the differentiation theorem. Now, let's do the integration theorem. So the integration theorem says if I have a piecewise continuous function, so this is differentiation theorem. Let's do the reverse procedure. It says I can integrate term by term if I start with a piecewise continuous function. So the tent function will equal 4 over pi. I'm integrating the square wave term by term, the sum over n odd of 1 over n. Antiderivative of sine nt is minus cos nt over n. And then there's an additive constant. So you'll notice what I've got is the sinusoidal part of the 10th expansion, which is a minus 4 over pi, the sum over n odd of 1 over n squared cosine nt. This constant is my a naught over 2 for the 10th. And the reason I wanted to do this is because to figure out a naught over 2, and that'll depend on which antiderivative you're getting. So for the 10th function, it's just the average value and you can compute the average value by an integral, or you can just look at it. The average value of that function, which varies linearly from 0 to pi, is pi halves. And so you get the Fourier series for the 10th function. Okay, so this will come up in your homework. When you're finding magic formulas, which is the last thing I want to talk about today. So, because they're cool. So here we have the formula for the 10th function. We know from our convergence theorem that it converges at every place where our, if we have a piecewise differentiable function, converges wherever the function is differentiable, and if there are places where it's not differentiable, but it's piecewise continuous or continuous, it'll converge to the average of the left and the right limits. So in particular, tent of 0 must equal 0. But if I plug tent of 0 into the Fourier series, I get pi halves minus 4 over pi, the sum over n odd of 1 over n squared times cosine of 0, which is always 1. So if I stare at this, I will see that 4 over pi times the sum over n odd of 1 over n squared is pi halves. I'm solving for the series. Then when I multiply by pi over 4, I get pi squared over 8. And that's a true fact. 1 plus 1/9 plus 1/25 plus dot 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 is pi squared over 8. Right? That's like 9/8 or something. A little bit more. Okay, here's another one we can get from the square wave. So this Fourier series converges everywhere. At the jumps, it'll converge to 0, which is the average of the left and the right limits. And that's from general theory. And from the formula, the signs are all 0 at multiples of pi anyways. But let's plug in what happens at pi halves, which is the place where the function is differentiable. Well, at pi halves, the square wave is 1. And on the other hand, it's 4 over pi, the sum over n odd of 1 over n sine n times pi halves. Well, sine of n pi over 2, and I could just leave it in there, but as a number without explicitly evaluating it, and that could be practical. But anyway, if n is even, I always get 0. If n is 1, I get sine is plus 1, and then I can add on any 4 times an integer, and I'll be adding on 2 pi to the n pi halves. So then, so it's 1 if n is 1 plus 4k, and it's minus 1 if n is 3, which gives me sine of 3 halves pi, or 3 plus 4k. So what I get here is 4 over pi. When n is 1, I just get 1 over n. When n is 3, so I get 1. When n is 3, the sign is negative 1, so I get minus a third. And when n is 5, I get plus 1/5, and so on. So the alternating series, which converges because it's a decreasing term series, is pi over 4. It's like 0.75 or something. How's that for magic? Okay, so the upshot of today's relatively shorter material is that Fourier series are unique, and I explained what that meant on the first page. If you start out with a function given as a Fourier series, that's its Fourier series. It's easy to differentiate and integrate Fourier series because you just do it term by term. And so if you start out with continuous and piecewise differentiable, you can differentiate term by term, and you get piecewise continuous. And if you start out with piecewise continuous, you can integrate term by term. And what you get when you integrate may or may not be 2 pi periodic. Okay, and then I guess the last thing, we did a couple examples of the fact that Fourier series contain magic summation formulas. And this was our summary for today. And we're done.